Okay, so let's get started with section 3.3, and this is going to be an introduction to logarithmic functions. And we shorten that logarithmic term down to log, and that's what you'll find on the calculator. Okay, so convert between logarithmic and exponential forms. So one way of looking at this is that basically you have a y is equal to b to the x, b greater than 1 for what I'm looking at here, increasing functions, and we looked at that last week. So f of x is equal to b to the x. It's a function, passes the vertical line test. It's a one-to-one function because it passes the horizontal line test, and one-to-one functions have inverses. Okay, so in order to graph it, I would do a nice little, here's a y is equal to x. And then this would be symmetric here, symmetric about that line. That's what this logarithmic function looks like. Okay, so if you're to each one, so if I have a f of x is equal to 2 to the x, I have a corresponding inverse. Okay, and what I would do is call f inverse x is log, this is 2, this is 2, there. That's that particular inverse, okay? The graph f of x is equal to, let's go 3 to the x, has its own inverse. That inverse is log base 3 to the x. This is the exponential base 2, log base 2. Exponential 3, base 3, log base 3. These two are inverses. So each one of these has, every time I do an exponential, it has its own very unique inverse, and that's how we keep up with the different ones. Okay. So this is basically one way we're going to kind of back into this thing by going through the slides. Okay. So here is this logarithmic function. If x and b are positive real numbers such that b is not equal to 1, then this function is called a logarithmic function with base b, and this is equivalent to b to the y is equal to x. So here's kind of the inverses I'm swapping, but this is basically the way I look at this is saying here. This is how I kind of do it. I have some number I want to represent as some power of the base. I want this to be some power, okay, of whatever base it is. I want to represent n as a power of b, as a power of b, the base. What would that power be? The log of b n is equal to that x, okay? That's what these two equivalent are saying over here. Okay, and we'll look at going back and forth between here. Okay, so let's just go through here. Okay, and some of these you're going to naturally be able to pick up. I want to represent, so here's kind of how I'm looking at this thing. I have a base 4. This is equal to 2. I want to represent 16 as a power of 4, and I can do this with any numbers, and we'll look at that in a minute. I'm saying I want to represent 16 as some power of 4. What is it? 2. 4 squared is equal to 16. This is the equivalent relationship, and we'll kind of go back and forth between these two as we run along. Okay? Let's do another one. So if I do log 5, 0.2 is equal to negative 1. Again, remember I did the inverses. These were the inverse things. Here's the function. Here's the number. They're kind of equivalent for there. Okay, going back and forth. Okay, so here I want to represent 0.2 as a power of 5. What is it -1. That's the log of this thing. So here, if I started, I go back, in the graph. But this is 1 over 5 to the 1. That's the negative end split. And if I do 1/5, that's 0.2. So I'm representing this number as a power of the base. But what do I have to raise that power to? It's -1 in this case. Okay. So this is basically equivalent forms from this to this. Both of these, this is the same as this, back and forth. Log base 8, logarithm base 8 of 1, that's equal to 0. And this is going to be that general thing. Anytime, so let's see what this is. I want to represent 1 as a power of 8. And the only way I get this is that's 0. The log of 1 to any base is going to be equal to 0. We'll see this later on as a property that I have any base, and if I take the log of 1, that's going to be equal to 0, because the only way this is going to be true, 1 is equal to b, what power for any number? That's the 0. So we have a final log of 23, log of 1 to the base 23. Again, this one is just 0 because I want to represent 1 as a power of the base 23. What would it be? The only way that could be is a 0. Yeah. All right. So here's a couple more. Some of these things we can just kind of observe and say, well, that's a power. We can know how to do this. Let me kind of do this thing again. Write each equation in exponential form. This is the log form. And then it says convert this over to the exponential form. Again, the easiest way that I see this is by saying, I want to represent this number as a power of 3. What is it? What is that power? 2. Okay, this is the log form. This is the exponential form. Okay, and they go back there. They're those inverses of each other, and each base, that's the base. Okay, and this is like the inverse of this. This is the inverse of that. Okay, so let's kind of move on. Here now, this goes from, these are exponential equations, and I want to write them in the logarithmic form. Okay, again, these go back and forth from one to the other. Okay, now I want to start with this exponential, and I want to write it in its log form, and I'm going to go sum of log because I've got an exponential, write it as the log. Here's the base. This is the number now. This is the number, okay? So, and I'll show you kind of rewrite this thing like I did before. I want to represent 16 as a power of the base. What is that power? That's the 4, 2 to the 4th. 2 times 2 is 8. 2 times 2 is 4, times 2 is 8, times 2 is 16. I'll get it right in a minute, okay? So from exponential, I rewrite this. Here's the base. That goes there. This is this, and here's the number. Okay. 27 cubed root is equal to 3. Okay, and I want to write this just like this. So the log, what's my base? This is the one that I'm raising to a power. So now this is the base here. What is the number? This is 3, and that's the exponent. Okay, so this way is actually easier for me to go back. I want to represent 3 as some power of 27, and what is that power? That's the 1/3. Okay. I want to represent 3 as a power, I want to represent, 3 as a power of 27. What is it, that 1/3? Okay. That's the equivalent log form of this exponential form. Base and base. I want to represent 3 as a power of that base. What is it? That's the 1/3. Okay. Let me continue. So let's see, evaluating logarithmic expressions. And I want you to do this with your calculator. So I want to represent, should have been like this. That's just the way it showed up in the slide. But that's what they want to do and say, what is this here? Okay. Now, some of these you can just do by saying, okay, well, I want to represent 144 as a power of 12. And I'm going to write it to, well, we'll do that later. But here, I want to represent 144 as a power of 12. What is that? That's that number. Okay, and for ones that are just even powers or even roots, we can kind of work this out. So if we do on our calculator, if I've got 12, and if I represent that by 12 squared, what is that number? That matches the 144. This is I entered 12 squared. Okay, so this number is 2. This log is 2. It tells us what we need to do to represent this as a power of 12, what exponent it would be. Okay. What about this one? I want to represent 8 as a power. So I'm asking you what this is, what this number is now. What does this mean? I want to represent 8 as a power of 64. What is that power? And if I take the square root, since this is smaller, it can't be squared. So if I take the square root, if I go 84, let me clear, hold on. Second, if I do second square root and then do my 64, that would be 8. The square root of 64. So this in rational exponents is 1/2. You remember this is the very same thing as here, 64 to the 1. That's rational exponents. Okay. Now I want to do this. Let me go back up to here real quick. If you've got the the TI-36, if you go, I'm going to clear this out, and now I'm going to do this directly using this function. So if I go here, ln, if I re-trigger this, just re-hit, it cycles through ln and log, so one key gives me the same thing. ln, we'll talk about that later on, but this log, let me go. If I do it one more time, it lets me change whichever base I want to use. So let me kind of get this up here so you'll see. So what I'm doing, I'm hitting this ln log function, the same button, ln log, and then I do this, I can change the base. So for this one, I'm going to enter the 12 here as the base and 144. So I don't just have to guess, I can use my calculator. Then I hit enter, and that's the 2. That's the 2 that we did just by kind of working backwards. What would it be? Based on inverses, okay? And if I do this one, I'm going to go back here. I'm going to hit that 3 times to give me the one with the variable base. Not all the calculators are going to do this. But if I do this one, I'm going to do 64 for the base. And then 8 is my number. That gives me the 0.5, which is 1/2. Okay. So let's go through. Here's another one that we can do. This is pretty straightforward. So if I have evaluate this without a calculator, I'm asking myself, I want to represent this number as a power of 5. What is this? 5 times 5 is 25 times 5. And then I can check it. Yes, indeed. Second, let me see. Clear. If I do 5 cubed, I get my 125. 5 times 5 times 5. Yeah. So that would be 3. So the log of this is equal to 3. What number, when I raise 5 to that power, that number gives me the 125, and that's 3. Okay, so here I went to the calculator. And I had, so this one, sometimes we've got this on one key, had this, and then sometimes this thing is like that, depending on the calculator. But ln is the log, but it is a very special log to the base e. And remember the e was the 2.7128, You remember that was that number when we did this as x went to infinity. What did this go to? And it turns out closer and closer to this number when x was larger and larger. Okay, so this is a very special log function that goes with e to the x. So log e to the x. Okay. So let me do it in this way. So if I have a log base e, which is ln of e, of a number, that's x, that's saying e to the x is equal to n. Okay, that's what that is saying. Here, log, if there's nothing there, this is understood to be the base 10. Okay, so in this case, the log of n was x. This means n is equal to 10 to the x. And they're just using a y, but then I'm just kind of keeping it to the same number so we don't switch the variables, but that's okay. So log x to the y, but this I want to do the x so that this will be the same variable when we're using that alternate form, whatever that number is. Okay. And then finally, so this whole thing is the very same thing as this. But we drop the 10s, so if there is no base listed, that means it's 10. And the ln, instead of writing log e, this one shows up enough that it's just shorting to the natural log as this was the natural number. ln stands for the natural log. Okay, so some of these we can still do without evaluating, like going to the calculator. Most of them you will not, but these are just special cases where it'll be just like regular numbers. So what is the log of 100? Then I have to recognize first that this means log 10 of 100. And that means 100 to what number is equal to 10? I want to represent 100 as a power of 10. What is that number? 10 times 10. 10 times 10. 10 squared is 100. So this should be a 2, which means that is 2. It can also be negative results. So here I've got log 0.0001. Again, this is powers of tens, and tens are just exponents, right? So here I want to represent and find out what that is, what this log number is. But to help me, I say I want to represent 0.0001 as a power of 10. What is that? 1/10. So each time these are negative exponents, it's got to be a negative. So this would be a -1, which would be 1/10, 2, 3, 4. That would be -4. So this is -4. Okay. So that is from a negative point of view. And again, if I went over, let me take the 30. So if I did here, if I went to log, and if I said 0.0001, that would give me the -4. And why -4? Because 10 to the -4 would be equal to that number. That's what the log does. Yeah. So it says, what is ln of e to the -3? Okay, what is the ln of e to the -3? Now, this is one of those thought-producing ones, and it says, I want to know this number, but now what does this mean? That means I want to represent e to the -3. This is understood as some power of e. Well, what is that power? Well, it turns out that's just that, right? This is the only way. It's a one-to-one function. There's only one value that's going to give me these things. So my question mark is the -3. Okay, so this is -3. And that works for the same thing as any of them. Here's ln e to the 10. Again, I want to represent e to the 10th as some power of e. That's what that base is for this. What is it? It's got to be that 10. Okay, so this is just 10. That's going to be one of our properties. In a little while, we're going to kind of list out some things, and we'll be able to do that. Okay.